Look around, and you will notice that certain objects feel perfectly balanced. In mathematics, this balance is defined as symmetry, the presence of identical proportions within a single object. We identify symmetry when one half of an object acts as a perfect mirror reflection of the other, or when the entire shape remains visually unchanged after a specific turn or flip. When we find a line that splits a shape into identical halves, we call it the line of symmetry. If you were to fold the shape along this exact axis, the two sides would overlap flawlessly. Nature often follows this rule. When a vertical line drops down the center of a butterfly, the left and right wings are revealed to be mirror images, proving the creature has a clear axis of symmetry. We verify symmetry by proving that two halves are identical reflections across a specific axis. To move past simple visual intuition, we use precise methods like the folding test to discover exactly where these lines of symmetry exist. If we attempt to fold the letter A horizontally across its middle, the narrow top point misses the wide legs at the bottom. Because the edges do not align, this horizontal line is not an axis of symmetry. However, by folding along a vertical midline, the two sides overlap perfectly. This successful test confirms that the letter A has exactly one vertical line of symmetry. When you cannot physically fold an object, mentally simulating this precise overlap is the most reliable way to verify if a shape is truly symmetrical. Consider a square. Because all its sides and angles are equal, it has 4 lines of symmetry: vertical, horizontal, and 2 diagonals. As it rotates, it returns to its original appearance 4 times in a single turn. A standard rectangle, however, has only 2 lines of symmetry. We can verify the vertical and horizontal axes through a simple fold. While a square allows for diagonal symmetry, a rectangle does not. When we attempt to fold along this diagonal, the corners miss each other entirely, sticking out rather than overlapping. This also limits its rotation. The rectangle stands tall at 90 and 270 degrees, meaning it only matches its original state twice during a full rotation. Even though both shapes have 90-degree angles, the rectangle's unequal side lengths restrict its geometric balance. We see this relationship between side length and symmetry in triangles. An equilateral triangle has 3 equal sides and 3 lines of symmetry, while an isosceles triangle has 2 equal sides and just 1 line. A scalene triangle with no equal sides has 0. If increasing the number of equal sides adds more axes of symmetry, consider the circle, a shape where every point on the boundary is defined by its distance from a single center point. Because of this constant distance, every diameter we draw through the center creates 2 identical halves. This means a circle contains an infinite number of symmetrical axes. This continuity applies to rotation as well. As the circle spins, its shape remains identical at every degree of the turn, giving it infinite rotational symmetry. Understanding these principles allows us to categorize any shape based on its balance. Symmetry provides the physical framework to analyze the geometry found in everything from a simple leaf to a complex bridge.